that means that, since the instructions per microjoule is decreasing, then the range at which you can power that fixed workload is gonna scale exponentially. But because you have this freeze formula with the square root in it, the exponential is actually half of the underlying exponential of instructions per microjoule. So put that on a plot. This top plot is instructions per microjoule, again for just empirical microcontroller data over the years. When you kind of compose it with freeze formula, the prediction you get is that, for this just sort of arbitrarily selected workload, if we say that's our minimum workload, we need to be able to power that to do anything, then the range at which you can power that workload is also going up exponentially, but with a scaling exponent that is half of the underlying one. So that's predicting that range should approximately double about every 4 years. So if that's true, that's very good news for this sort of work, because it means that even though WISPs and devices like that sort of barely work right now, they should get a lot better if you're interested in doing the same workload. Okay, so now I'll talk about some ideas for increasing the efficiency of these low power situation harvesters. So Maxwell's demon was posed as a kind of paradox of thermodynamics. The idea was you have a little intelligent being, which in this example has a little door it can open. It waits for fast particles coming this way, and it'll open let's say fast particles coming this way, it opens the door, and slow particles going the other way. After a while of opening and closing this door, it can create a temperature difference. And it was a challenge to explain the problem with this. People thought about mechanisms for doing this, and it seemed like there were various ways you could do it where the energy harvested from this initially equilibrium set of gases, it seemed as if this was a way to produce free energy. So a lot of work has gone into analyzing this. One of these is a specific model called Smoluchowski's demon, which is basically a trap door, spring-loaded trap door. When you do the analysis, you find out that if the gases start at the same temperature and pressure, you can't extract work as you'd expect. People have proposed more detailed mechanisms as well to try to understand this further, where you divide a chamber in two and sense whether there's something on one side or the other. Now, from our point of view, energy harvesting is about the situation where there actually is energy in the environment to be harvested. So all these demons, if there actually were a temperature difference in the beginning, could certainly make use of that to power things. So the way I'm thinking about this is, imagine we have these demon-like devices, sort of like people imagined for explaining these paradoxes, but we actually build them and we put them in a situation where there is power to be harvested, like near an RFID reader. Specifically, if you replace all these, here's one implementation that Alanson and I have explored. If you replace these diodes with transistors, and you look at the very low voltage region, this is a diode IV characteristic, and this is a transistor IV characteristic. In the very low voltage region, the slope of this is much higher than the slope down here. So the idea, or a specific thing we've tried, is in simulation, you take an input waveform, you convert it into a square wave, and then you use, in this case we have an in-phase and an out-of-phase square wave. You use that to actively switch those transistors, and then you find, at low, at very low voltages, you get more efficiency. This plot shows a passive harvester running for a little while, and then the active harvester being turned on just arbitrarily at a certain time, and you see a big bump up in power produced. You can actually combine both of these together. and have something that smoothly switches between passive and active. Let's see. So, but what that brings you to, of course, to control those transistors, you need some active circuitry to do something. Okay, Kevin has given me the axe here, so I will just quickly conclude. Where I think this is potentially going, that's interesting, is if you look at a WISP today, as soon as you turn the power on, it wakes up. If you turn off the power, it goes to sleep typically. But if you think about biological systems, that's true of microbes. They can when they run out of energy, as soon as you can bring them back to life. But all other creatures, if they run out of energy, they die, and that's catastrophic. So I think it's interesting to think about power harvesters that have that same property. They have some store of energy. They use that to run an active energy harvesting system, and if they run out, that's it. So I think that might be an interesting model for more complicated power harvesting systems. So thanks very much. Sorry for going over.
Really cool work. I've got a quick question. Praval at UC Berkeley. The analysis that you did on Moore's law and lifetime of these things, I was wondering, does that fall prey to some extent to Andal's law, which is you can get increasing computation, but if you can't get the data off, you're in trouble, and it's the radio that really kills you?
I think that's an interesting thing to think about. I think one of as Kevin pointed out earlier, one of the nice things about WISP is that if you're in range of the reader, communication is sort of free. You can think of it that way. So I don't know. I haven't thought about that in detail, but you do have to think about the sort of economics of backscatter communication, and I don't know. We should talk about that. Thanks.
That aren't necessarily focused on WISP. They're just alternative methods for harvesting power. So they're going to be ambient power harvesting, and then this wireless resonant energy link. So what am I talking about here? So warp is the idea of powering or harvesting power from TV signals. Giving signals from the back here. I'll try one more time. Okay. Or I'll just speak loudly, whichever one. So we're talking about harvesting TV signals, right? And then so this is low power microwatts of energy. And I'm going to show some of the experimental results. The other one is a high power version, so we'll call this WREL, and this is tens of watts. So these chromatically two different realms here. And then so we're having a deliberate power source that we actually have a transmitter, and I'll show some results from that as well. Okay, so Josh kind of outlined what we normally think here about RFID. So we have an RFID reader and a tag. We get about 10 meters of range. We get 20 microwatts in. So that's kind of like typical baseline. So what do you need for that sort of thing? So you need an antenna. There are certain characteristics about wavelength that you certainly have to have for size. You have to have a shape. You need to have a DC-DC converter. And you have to keep in mind a few things. You have to worry about the input impedance and the output impedance of that DC-DC converter. Typically, you need to have an energy storage device. And there's lots of different ways to do that. So that could be a super cap. You could have a battery. It could be just a small capacitor. And then you have to have a regulation side so you can start powering your load. So you need these functional blocks to match, to effectively do this. So if we start thinking about urban environments, there's basically this ubiquitous power source going on all the time, right? And we normally think about this as signal level stuff. So like, TV signals or radios or Wi-Fi. And nobody's really thought about this as power level, as something we can use for power. So what's different here is that as Josh also pointed out, is that the power consumption of semiconductors is going further and further down. So now we have an opportunity to use these things for something useful, right? So 50 years ago, there was no possibility. And in the future, there'll be a lot more possibility. So what's out there, right? So there's Wi-Fi, and here's this little map of all the open Wi-Fi access points around, or not open, but Wi-Fi access points around Seattle. So there's a huge dense coverage, but there's not much power. There's only 20 milliwatt or 200 milliwatts. You can kind of go up the power scale here, so you can think about GSM, not the same scale here, but now we're talking about 100 watts of transmitter power. And you kind of go to the stream, who's the big players out there, who's broadcasting super large amounts of power. So now we have TV